Hello everyone! As you may well be aware of, the exam season is upon us, and with that in particular, stats exam is in less than a day. And in honor of that, I've decided to make a very quick, easy way to get through all of the stats syllabus in case anybody needs last minute revision or just to recover any of the topics. And because I really wanted to fit this in under half an hour, I'm going to stop talking now and just start explaining the whole syllabus, everything you need for this thing. Up first is Poisson distribution. It's used for events that have small probability of occurring by themselves, so they are classified within a fixed period of time. Say, the chance that I explain statistics to someone is small, but on average, I explain two concepts in a month. In other words, because the probability is so small, we use that set period of time in which we can count how many times an event occurs. In order to be able to use Poisson distribution, the events must be random, independent of each other, occurring within a fixed period of time, and with a constant probability of success versus failure. This means that there must be only two outcomes. In other words, I either explain someone's statistics or I don't. There is not partially explaining. It's written as x belonging to Poisson of lambda, where lambda is the mean number of events happening within our fixed period of time. It is also the variance of that number. If x has Poisson distribution, then mean and variance are exactly the same. Reason for this is because variance is classified as number of events times probability of success times probability of failure. As the probability of success in Poisson is small, probability of failure is close to 1. Therefore, the mean and variance are the same. However, if mean and variance are approximately the same, then it can be approximated with Poisson. It's important to make the distinction between when x has a Poisson, so mean equals variance, and when x can be used with Poisson, so mean is approximately the same as variance. Now, the formula actually used to calculate the probability that certain event occurs x number of times within a period of time is e to the power of negative lambda times lambda to the power of x over x factorial. As Poisson is a discrete distribution, rather say there is a whole number of events that can happen, when we want to calculate the probability of those events happening less than a certain number, we need to calculate the probability of each number in that range. Conversely, if we want to calculate the probability of events happening more than a certain number, because we can't make a list that goes into infinity and calculate it, we will take 1 minus the probability of events happening less than that number. Pay attention, this is not normal, so one of those has to have an equal sign. So either it's probability of x being bigger or equal than 4, or it's a probability of x being smaller or equal to 4. But there needs to be 4 counted in either one of those. Now, when it comes to approximations, Poisson can be used as an approximation for binomial. Say, if n is large and np is small, aka if n is bigger than 50 and np is smaller than 5, then we can use Poisson as an approximation. Because they are both discrete, there needs to be no continuity correction, and we set lambda to equal to np taken from the binomial, and then calculate as we would a normal Poisson distribution. On the other side, normal can be used as an approximation for Poisson if lambda is bigger than 15 or if lambda is large. In this case, both mean and variance are lambda, and because Poisson is discrete whereas normal is continuous, we need to use continuity correction. And then we just calculate as we would normally a normal distribution. Already on to the next topic, we have linear combinations of random variables. This is a very short topic of how expected value and variance of a variable change as it's multiplied, added to another variable, or added to a constant. When it comes to expected values, they change pretty much the same way that their value changes. So, an expected value of ax plus b, where both a and b are constants, is going to be a times expected value of x plus b. Expected value of x plus or minus y, where x and y are both variables, is going to be expected value of x plus or minus expected value of y. This obviously only works for independent x and y. When it comes to variance, though, it gets slightly different. So when we have variance of ax, where a is a constant, if it means a times value of a single x, then a will be squared, and it's a squared times variance of x. But if it means a sum of a different values of x, then it's a variance x, and a isn't squared. Also, when we have a variance of x plus or minus y, where both x and y are independent variables, variances always add up. Variances never subtract from one another. Now, a few more notes. If x has normal distribution, then ax plus b will also have normal distribution. If x and y have independent normal distributions, then x plus y has also a normal distribution. If x and y have independent Poisson distribution, then x plus y also has a Poisson distribution. Now on to continuous random variables. This is a pretty new topic in terms of stats curriculum, but a continuous random variable is a variable that can take any value in a given range. Probability density function describes the probability of the continuous random variable. And the easiest way to look at this is to remember that, for example, a graph of normal distribution is also a probability density function. So the area below the curve, below this function, or between the function and the x-axis, is the whole of probability, and it must equal to 1. Also, the function, or the probability, can never be less than 0. So the function must not go into the negative, below the x-axis. And those are going to be the two main terms that you're going to be testing whether something is a valid probability density function against. They're usually given either in form of this open bracket, stating what the function is like for each interval. It's unlikely that there will be more than 2 intervals, or it is going to be given in form of a graphic or a geometric representation on the page. Whichever way, it's important to know that probability of x being between any two variables is the area between these two variables, or an integral of probability density function between these variables. So, probability between the limits should be integral of our function between those limits, and it should always be equal to 1, because the probability that it can be any variable is always 100%. Also, this is a continuous variable, so probability of any discrete variable is always going to be 0. Because there is so many variables in this range that our value can be, the chance of any single one of them is very, very, very bizarrely small. So the probability is usually defined as between some two variables. Same thing as works for normal distribution. Now, if it's given as a graphic, it's good to, at this point, just apply the simple, pure geometric knowledge, looking at it and saying it's actually just a rectangle, so between these two variables, the probability is one side times the other. When it's given as a graphic, it usually tends to be simple form of geometry used. Now, expected value of x is the integral between the limits of f of x times x dx. Variance of x is the integral between limits of x squared f of x dx minus expected value of x squared. And both of these are in the formula sheet, so you don't have to remember them by heart, but you do need to know that they exist in the formula sheet and how to use them. Another important thing is the percentiles. 19th percentile is a value such that probability of x being below it is 90%. To find it, we need to set an integral between the lowest limit of x and a dummy variable and equal that to 0.9. If we are searching for a median, we will equal it to 0.5. For quartiles, we would equal it to 0.25 and 0.75 respectively, and that is most of the percentiles that you need to know. Also, it's unlikely to show up, but mode is the highest point on the probability density function. So if it's given as a geometric picture, you can really easily see if it's going to have one or where it's going to be. Now on to a slightly bigger topic, sampling and estimation. Sample is a part of the population that is drawn for testing, and it's usually used because either a population is too large to test, or the method of testing we are implying is destroying the members that are tested, aka if you are testing the life of batteries. As we measure how much each battery lasts, we are destroying the battery. It can't be used or sold anymore, so it doesn't make sense to be testing the whole population of batteries. This is also called destruction testing. Now, a sample needs to be random to be representative of the whole population, because biased sample is not representative or typical. For example, January, February, March are not representative of the weather during the whole year because they're all in the same season. Now, a random sample is selected in such a way that all possible samples of the same size have the same probability of being chosen. Now, one note, this doesn't mean that every random sample is unbiased or representative, because all samples have the same probability of being chosen. That means that the most biased, unrepresentative sample can still be chosen. So when we say unbiased later throughout the lecture, it means that although individual estimates vary, the process gives an accurate result on average. So it's unbiased usually. It doesn't necessarily mean that it's representative always. Obviously, the bigger the sample we use, the more representative it will be. Now, one way of drawing a random sample is by using random numbers generated by a computer or a calculator, and this might appear on the exam. And it's functioning in a way that each member of the population is numbered, and then a computer is given to produce a list of random digits. So say a population has 600 members. Because this is a 3-digit number, we are going to be taking chunks of 3 digits out of this list of digits given by the computer. So the first one is 587, and that is going to be the first member we choose for testing. Second one is 143, and that's our second member. Now the third would be 620, but this is above 600, so there is not a member with this number. Therefore, we are going to be taking out the whole number from the list. We are not going to be taking 201 as the next, no, whole 620 are going. And the next pick is 107, and that works fine. But then after it, 143, we already picked that one, so it's going. 588 is then our fourth pick, and we can take these 4 members or take more, it doesn't really matter. Important thing though is that once these digits were used to pick members, we can't use this same list of digits to pick more members, because then the numbers drawn aren't independent of each other. The sample isn't truly randomized unless every digit is used exactly once or 0 times. So all of the digits, all of the numbers chosen need to be independent from each other. They can't be used 2 times. Now, another important thing to understand is that sample mean can also be regarded as a random variable and with properties such that expected value of the sample mean is the population mean. Variance of the sample mean is variance of the population over n, where n is the number of members in the sample. Central limit theorem states that if X has a non-normal distribution, but sample size is large, then the distribution of sample mean of X is approximately normal, with sample mean of X being distributed with mean and variance over n of the whole population. One note here, when dealing with sample mean, central limit theorem doesn't need continuity correction because sample mean is not discrete. It's a continuous variable and therefore no continuity correction is used. If X already has normal distribution, then sample mean will have normal distribution too, and we actually aren't using central limit theorem. The parameters are still the same with mean and variance over n. Now, this was how sample mean is defined by the population mean and variance. And here is how population mean and variance can be approximated or estimated by sample mean and variance. So here is where unbiased estimates come into play, and unbiased, as we already talked, doesn't necessarily mean 100% representative. It means that on average they will be representative of the population, but individual estimates may vary. These results are also given in the formula list, but estimate for the population sample is the same as the sample mean. It's E sum of all variables over n, which is number of members variables in the sample. Estimation of variance is 1 over n minus 1 times sum of all variables squared minus sum of all variables, where this whole sum is squared, over n. They are, as I already said, in the formula list. You just need to locate where they are and remember to use them. You don't need to remember them by heart. Now, onto confidence interval. Because these are estimates and you might not be sure that it will necessarily be that precise variable, and because these are continuous variables, the chance of it being precise is tediously small. We can still construct confidence intervals. That means that if we have a 95% confidence interval, that means that we are 95% sure that the real population mean is within that confidence interval. So 5% chance is that it is not, and it is outside of our confidence interval. They're constructed by taking the unbiased estimate for mean that we have calculated and then adding or minusing that value of a certain probability times the standard deviation. Because our variance here is a variance of the sample, we will be using variance over n. So standard deviation is square root of variance over n. Now, as for what probability we are putting into our z value, when we have a 95% confidence interval, it is centered so that at each end there is 2.5% outside of our confidence interval. So the value right here is 97.5% because it is 100 minus 2.5. So the probability that we are putting into that value is calculated as 100 minus the remainder from our confidence interval over 2. So 100 minus alpha, if alpha is our percentage of the confidence interval, over 2. Now we can also use the same thing to calculate confidence intervals for population proportion, using the approximations for population proportion given at the very bottom of the stats2 section of formula sheet. And it is of the same base idea as the confidence interval for mean, just proportion replaced with mean, and instead of variance that we had for mean, we are using proportion times 1 minus proportion over n, and that is square rooted as variance would be usually. Underlying the distribution of any proportion is binomial, so this is also implementing central limit theorem. And last but not least, we have hypothesis testing, probably the most interesting part in this video. First off, hypothesis is something that we wish to test, an assumption, an idea of how much something is. Null hypothesis is something that is assumed to be true, that it had already been shown true in the past, or is logically true. For example, if you have a dice, you will assume that each side has the exact same probability of occurring as other sides until you prove that it's biased. So, alternate hypothesis is something that we suspect might be true, but we haven't shown it yet. Maybe we suspect a null hypothesis to be false, maybe something else has changed and that impacted the situation. So, this leads us to the next thing. We will perform some testing on a sample and we need to decide a significance level. I say we, but it's mostly decided in the questions already. A person that is testing this needs to decide a significance level. And this is a percentage of how unlikely something has to be for us to reject the null hypothesis. So, for example, if null hypothesis states that the probability of something happening is 3%, but it happened anyway, then we might suspect that null hypothesis isn't true. It depends on where we position our significance level. So, the smaller the significance level, the more precise we will be. And the higher the significance level, the less precise we will be. For example, if null hypothesis says something happening is 25%, but we reject it, then that's not really true, is it? Because 25% isn't that rare for something to happen. So, now that we have understood what the significance level is, there are two types of hypothesis testings. If alternate hypothesis simply disregards the null hypothesis and says, if this is in terms of mean isn't x, then this is a two-tailed test because direction is unspecified. So significance level gets halved and put at each side of the normal distribution curve. If alternate hypothesis has direction specified, so it either says mean is smaller than the mean in null hypothesis or mean is bigger than the mean in null hypothesis, then it's one-tailed and the whole of significance level is put on either one end, left if it's smaller, or the other, right if it's bigger. Now, usually in the question we will be given already a sample and what they got. And at this point, we need to find the probability of whatever was got happening. So, of probability that x is smaller than 2 or probability of it being bigger than 2. One important thing is because this hypothesis testing is referencing the continuous distributions. Even if the given distribution in the question is discrete, we still need to calculate smaller or bigger of the value we got. We can't calculate exactly that value. We can calculate that value and bigger, that value and smaller, but it can't be just one value that we are finding the probability of. Now, when we found the probability as we would by everything else, and it might use approximations or sample means or anything really that is covered in the rest of statistics. When we found it, if that probability is smaller than significance level or half of the significance level based on whether it's one-tailed or two-tailed, then we will reject the null hypothesis. We don't write except alternate, we just write statement in terms of null hypothesis, either reject if it's smaller than the significance level, or if the probability of the given value is bigger than the significance level, we accept the null hypothesis. And then we state in terms of context how there either is or isn't significant evidence to suggest that alternate hypothesis is correct. And we need to put that alternate hypothesis in context. So if alternate hypothesis says mean number of people walking down the street is smaller than 5, then we would say if we have got reject HO, there is significant evidence to suggest that the mean number of people walking down the street is smaller than 5. It must not be a definite statement such as the mean number of people walking down the street is smaller than 5. No, it must always be within context and certain level of plausible deniability, let's put it. Because we haven't actually tested whether alternate hypothesis is true. We have tested whether the null one isn't. An alternate hypothesis is still only an assumption. Now, the values under which we would reject HO are called critical or rejection region, and the values under which we would accept HO are called acceptance region. If we are searching for a rejection region outside of a specific test, we would start from the smallest value and we would slowly build up until the probability of that value and those before it, so that value and smaller, appearing surpasses the significance level. When it does, we take the one before it, that one and all smaller than that are our critical region. Similarly, if we are testing whether mean is bigger, then this would start from a significantly big number and then go smaller until we have a probability that is bigger than the significance level. Same principle. However, when we do this hollow hypothesis testing, we are prone to errors because its significance level, it is not certain. There are two types of errors. Type 1 error, which is false positive, which means that we have rejected HO when it was true. Probability of type 1 error is the probability of X being in critical region. Usually this means that it is a significance level, but if it's a higher marked question, they usually want you to find the critical region and then find the probability of X being in it. Why this error is possible to make is that at the start we say, if something that is unlikely to happen by null hypothesis happens, then I will reject it. But it is still somewhat likely that it happened by the null hypothesis. So, as much as we say significance level, that is the chance that we've made a mistake and we are rejecting it when it's actually true. Type 2 error is false negative. This means that we have accepted the null hypothesis when it was not true. And if we are asked to calculate type 2 error, we're usually given a true medium. Because HO medium is not true, we can't calculate using that. So we usually said, given now that the true medium is this, find the probability of a type 2 error. And probability of a type 2 error is the probability that X is outside critical region or that X is inside the accepting region, given that the true medium is used. So we would calculate exactly the values that we have in the acceptance region using our new medium, and that is a probability that we have made a type 2 error. And that's it for sampling. And that will be all. We made it just under 30 minutes. If you made it this far, thank you for watching. I hope you found it helpful. If you have any questions or specific content you'd like to see in regards to maths exams, let me know in the comments and see you next time.